Well, I'll assume the others will show up in just a few minutes. So last time, so we've got 2 more lectures left. So we'll finish up the book. I think we're right on target to do that. So last time we talked about different types of waves. For the remainder of the semester, we're going to concentrate on plane waves. Again, important for 2 reasons. They do arise in practice, and if you're far enough from the transmitter, you can treat the portion of the wave, regardless of whether it's spherical or cylindrical, as a plane wave as far as your receiver is concerned, as long as your receiver area is not immense, which it typically isn't. So unfortunately, we have to go through a little math to derive some results on plane waves. I'm not going to actually continue this discussion next time, but I want to start with kind of where we were last time. We had Maxwell's equations. I think I had this on the board. But Maxwell's equations lead to a pair of wave equations. Del squared E tilde plus beta squared E tilde is equal to 0, and del squared H plus beta squared H tilde is equal to 0, where beta is our phase propagation constant. It's omega square root of mu epsilon. And then now we've restricted ourselves in a number of different ways. One, we're in the phasor domain. Okay, we'll get back to actually the time domain today. But so we don't have to worry about the time dependence and what we're doing today, just the spatial dependence. Now, this is a wave equation in 3 dimensions compared to the wave equation we were looking at the beginning of the semester, I think back in chapter 1 actually, where we just looked at the partial derivative with respect to z and talked about propagation in the z direction. We took that same approach with transmission lines, aligned our transmission line in the z direction. So we'll make some simplifications here as well. The other thing is this is source-free region. There is no free charge. There is no current density. So again, it doesn't apply within the antenna, transmitting antenna itself, but away from the antenna. And we're assuming that it's lossless. And that's a simplifying assumption. The media is lossless, that so that means for us that, well, the conductivity of the material is 0. It means for us that there's no decrease in amplitude with either the electric or magnetic fields. And we know that's not true in a practical problem, but it's a great simplifying assumption, and it works pretty well in free space. Actually, it depends on the loss depends on the frequency quite a bit. So we're going to start. We will assume E and H have constant magnitude and phase in a constant plane. And this may seem pretty restrictive, but it's really not that much more restrictive than saying we're dealing with plane waves. Plane waves have would have this constant phase and magnitude across the phase front. So it seems pretty restrictive to say, well, we're only going to deal with waves propagating in the Z or phase magnitude phase constant in the Z plane, but it really could be any plane. So it was just like when we worked with coaxial cable and aligned our cable along the Z axis and got results, but those were valid regardless actually of the orientation of the cable. So the same is true here. We can just orient our coordinate system so that the phase fronts are in the Z plane. So it's not really restrictive at all. But what it does mean with regard to the spatial derivatives is that there is no change in the E field in the X or Y direction. Well, that's true for both the E and H fields. So all these partial derivatives are 0. Okay. So this reduces, for this special case, this reduces our 3-dimensional wave equation to a 1-dimensional wave equation, something we can handle. And you can take a similar approach for spherical waves or cylindrical waves. The wave equation for E becomes partial derivative, second partial derivative with respect to Z of E of X plus beta squared E of X. Now I'm going to convert to, this is my notation is failing me here. This E is actually a vector. In the past, I've represented a vector with a bar over it. And now I'm trying to represent whether something's a phasor by putting a tilde over it, but I'm not writing down both bars and tildes. In the textbook, he uses boldface to indicate whether something's a vector. So E here is a vector. This is the X component of that vector. And so this wave equation actually becomes 3 wave equations for the X, Y, and Z components. EZ plus beta squared, EZ, where, so it's really taking this wave equation, writing it out in 3 dimensions, and then really equating the X component to 0, equating the Y component to 0, and equating the Z component to 0. So our general, what these things represent. Okay. So again, the tilde represents a phasor. And you have to kind of tell by context whether it's actually a vector or just a simple function. In this case, these EX, EY, and EZ, they can be functions of Z. And they're not functions of time because they're phasors. We'll jump back into the time domain in just a bit. But they may be functions of Z. They're not functions of X and Y because we set up the way we set up the problem, saying that we've got their plane waves and the phase fronts are in the are parallel to the XY plane or in a constant Z plane. So then if you jump back to Maxwell's equations, the source-free phasor form of Ampere's law which is del cross H is equal to plus j omega epsilon E tilde, and that's in the phasor form. And the Maxwell Faraday equation which is del cross E is equal to minus j omega mu H, can be used, and I'm not going to go through the derivation. So see the textbook, it's not hard, it's just several paragraphs long. Okay. To show that the z components of these waves with constant phase fronts that are in the z plane, that the z and h, the z components of E and H also have to be 0. So our three-dimensional wave equation reduces at this point to a pair of wave equations for our electric field. And we have the same set of wave equations for actually our magnetic field intensity. So what this says at this point, okay, it's easy to get lost in all this complicated vector mathematics. But at this point, starting with the assumption that we're working with plane waves, we found that E, and then similar relationship for X, the electric field will just have X and Y components. It can't have a component directed perpendicular to the phase front. So our phase front, our constant plane of phase is the constant Z plane or parallel, or an XY plane, and our magnetic field only has components in that plane. I'll try to draw a picture of that in just a bit. Okay. Now, this is actually, again, these are one-dimensional wave equations. And we solved back similar to equations we dealt with in chapter 1 and 2. We first looked at the wave equation and talked about propagating waves in chapter 1, and then actually propagating waves in transmission lines in chapter 2. So the general solutions are E of X tilde is, this is just a constant, but it may be, this represents a term propagating in the plus Z direction, the one with the minus sign, and then EX0 minus would be, this term corresponds to propagation in the negative Z direction. These may be complex constants, and they're determined actually by the boundary conditions. At Z equal to 0, both these exponential terms are 0, and we've got the sum of these two constants. So based on the boundary conditions at Z equal to 0 and one other point, we can determine what these propagation constants are. And similarly for my Y component, it's the same equation. So we come up with the same general solution. And again, our general phasor would be EX plus Y, UY. So this is the vector. And then these are functions of z. They're only functions of z at this point. Okay, they're not functions of time, again, because they're phasors, and we've said because they're plane waves, they don't have x and y components. You can go through the same procedure for h. With the result that h of x is h0 plus e to the minus j beta z plus hx0 minus e to the plus j beta z, and hy tilde is hy0 plus e to the minus j beta z plus hy0 minus e to the plus j beta z. And again, h consists of just x and y components. And I realize it's hard to tell my tildes from my carets that I'm using for my unit vectors. Again, my notation has broken down a little bit. But these are the same equations we ran into back in chapter 1 and chapter 2. But kind of to summarize, and this is probably the most important point here, is that E and H lie in the xy plane, while propagation is in the z direction, either plus or minus z direction. So I'll try and draw a picture of that as best as I can. So here's our xy plane. And what we're working with now is we're assuming planar phase fronts like this. So I'll draw this is a plane that's parallel to the xy plane. And like I drew last time, there would be multiple phase fronts. All planes corresponding to points at which the phase is the same and the magnitude of the fields are the same. Now in this plane, our electric field intensity has to lie within the plane. That's what these equations tell us. Even though the propagation is perpendicular to the direction of this electric field. I'm going to draw H actually also lying in the plane. I'm drawing it at a right angle actually to E. We haven't proven that yet, but that is the case. We'll see in just a bit that E and H both have to lie in this plane, and that they are perpendicular to each other. We'll also see that they're perpendicular, they're individually perpendicular to the direction of propagation, which is in the z direction. So, and if you think about throwing a pebble into a pond and creating the cylindrical wave fronts, the rings that you see are the points of constant phase. And then, but those rings grow larger and larger. They travel out from the point at which the stone was dropped into the pond. So the direction of propagation is perpendicular actually to the phase front. That's true for cylindrical waves, spherical waves, and it's also true for these planar waves. So if you could imagine, visualizing this, which I have trouble visualizing this in 3 dimensions, but the propagation is actually perpendicular to the plane in which the fields. We'll talk a little bit more about this next time, and I'll try to do a little better job of showing some pictures of this. Now we want to try and get, right now we just have this general relationship that E and H have to lie in the XY plane, propagation in the Z. We'd like to have a relationship between E and H, and fortunately there is one. We can use Maxwell's equations again. The Maxwell Faraday equation, or MFE, can be applied. These are the curl relationships. Again, I'm not going to go through the text, so I can jump to the result. Can be applied to show that E and H are perpendicular and also show that E cross H is in the direction of propagation. And that's consistent with the picture I've drawn here. And this E cross H, it gives us the direction of propagation. Okay, remember which comes first. It's E cross H. We'll use it just a bit actually to determine the direction of H. Now, if we've got E, there's actually, knowing that H is perpendicular, I've drawn E in the X direction, but again, we could rotate the plane, so E could be in any direction. But we do know that H is going to be perpendicular to E. But it could be Y directed, or it could be plus Y directed or minus Y directed if E is in the X direction. Both of those are correct. But if we know the direction of propagation is in the Z direction, then H has to be in the Y direction. If it were in the negative Y direction, E cross H would give us propagation in the negative Z direction. So your right-hand rule and understanding this cross product is important. There's another really important result, and that's the ratio of the magnitudes of the two fields is equal to a constant called eta, where eta is equal to the square root of mu over epsilon. And this is called the intrinsic impedance. It has units of ohms, and it's an impedance. Remember, E is actually volts per meter. One to express the units for E in a couple different ways, but one way is in volts per meter, and H is in amps per meter. So the ratio, the meters will cancel out, you're left with volts per amp, which is ohms. So that is an impedance. The other thing, we're working in general material at this point, so not necessarily free space. But if we are in free space, the intrinsic impedance of free space is eta 0 square root of mu 0 over epsilon 0. That's 377 ohms. This kind of plays the same role as characteristic impedance did for transmission lines. Characteristic impedance was, you know, the ratio of voltage to current there, and it was a function of the geometry of the transmission line. And this is also a ratio of, you know, the electric field intensity to the magnetic field intensity. And you know, it depends on the medium. But here's an example of the type of problem that at least we can work now. So if I give you a phasor for the electric field intensity. So in this case, we know that it's in the x direction. We know that it's actually propagating in the plus z direction. That's because of the minus j beta z. If that were a plus j beta z, it would tell us it's propagating in the negative z direction. So in free space, the problem is to find the corresponding h. We've got enough information to do that. So we know h is perpendicular to e. So e is in the x direction. So if h is perpendicular to it, we also know h has to be perpendicular to z. So it's either plus y or minus y. So which is it here? It actually corresponds to that figure there. Okay. I know E is x directed. We're propagating in the plus z direction. So H has to be y directed. So part of this is actually just putting that piece together, figuring out whether this is plus y or minus y. Now, if x were in the y directed, h would have to be in the negative x direction, right? If I rotated, so E were in the plus y direction, h would have to be negative x directed so that the cross product would still be in the positive z direction. So, or more generally, E might have x and y components, but we can determine the direction of h just from knowing the direction of propagation. Okay. And then I know we have this, h will have the same functional form. It is also propagating in the plus z direction. And then we also know, I can also find the amplitude here. It's 10 over the intrinsic impedance. Might remind you of Ohm's law. In this case, since it's free space, it's 10 over 377, or 0.02653, and it would be amps per meter here, actually, since the 10 would be in units of volts per meter. So putting it all together, 653 e to the minus j beta z would be the answer for h. Okay, so let's jump back into the time domain now to see what's going on there. see what the E and H fields are. So at this point, we have our phasor now. In this example I just worked, the E0 was a real constant, but in general E0 may be complex. E0 have a magnitude and phase, so we'll call it phase angle psi. Okay, so in general, it may be a complex number in the phasor domain. And similarly for H, E0 over eta, e to the minus j beta z. And although it looks pretty restricted, it is actually fairly general, because if I have propagation in the x direction, I would replace the z with x, and then my E and H field have to be z and y directed. Or it might be propagation in an xy direction, and then using these cross product rules, I can figure out the directions of E and H. The other thing here looks with propagation in the z direction, it's restricting E to be just in the z direction appears to be fairly restrictive. I can just rotate the xy plane so that my x-axis is aligned with the direction of E. So I'm being fairly general here in terms of my choice of coordinates, where beta, our phase propagation constant, depends on the frequency, the permeability, and the permittivity of the material. And then the other constant that appears here, eta, is U over epsilon, is the intrinsic impedance. So going back to the time domain now. And so this is just a bar. I take the real part of, formally this is how we do it mathematically. We generally don't write it out that way, but E would just be x E0 cosine of omega t minus beta z plus psi. Again, E is given by this, E0 is this complex constant, so the phase angle of our complex constant appears in our cosine. So this is just like working with phasors in circuits, right? That our phase angle here is e to the minus j beta z plus j phi, and then E0 e to the j phi forms my E0 constant. So those both come right into my phase angle here in my expression. So this is my vector expression for my electric field. It's x directed, but it's propagating in the z direction. So what I mean by that is the E field is pointing in the x direction, but it's sinusoidally varying with the phase fronts all are in constant z planes. And we have a similar result for H. It's going to be perpendicular to that. Its amplitude is going to be the amplitude of E divided by our intrinsic impedance. And we'll have the same phase angle then, as long as the intrinsic impedance is real. Now, we've looked at equations like that earlier in the semester, and I'll just remind you of a couple of equations. These are waves with the wavelength is related to the propagation constant. It's just 2 pi over beta. So that's the wavelength. And then the phase velocity, the rate at which the phase fronts are propagating outward, is equal to omega divided by beta. Okay, so omega is our frequency of radians per second, and beta is our phase propagation constant. So both those come right out of this cosine equation. It's what's multiplying t divided by what's multiplying our distance, the ratio of omega to beta. Well, since beta is omega times the square root of mu epsilon, our phase velocity is just 1 over the square root of mu epsilon. In free space, the phase velocity is 1 over mu 0 epsilon 0, and that's 3 times 10 to the 8th meters per second, which you probably recognize. It was this discovery that by Maxwell that led to the conclusion that light waves are actually radio waves. They're special only in the sense that we've actually got radio wave receivers built into our heads, right? Our eyes. We can detect a particular range of radio frequencies. That's the only reason really that light waves are special to us. In every other sense, they're regular radio waves, just like AM, FM television waves, but we don't have built-in receivers in our bodies for picking up AM and FM waves. So it was this discovery that said, oh, light waves are just like all this, all grouped together now and called electromagnetic radiation. So we generally call this the speed of light, right? But it's really the speed of a radio wave, any electromagnetic wave in free space. Speed of light, which we generally designate as c. Okay, just in other media, if you're not in free space, the phase propagation velocity is c over relative permeability times the square root of the relative permeability times relative permittivity. Since these are always greater than 1, the phase velocity in any other media other than free space is going to be slower than the speed of light. And then we also have from above, and you can get that directly from these 2 equations, that lambda is the phase velocity divided by the frequency. So, and from that you can get, well, since the phase velocity is always a maximum in free space, which is the speed of light, the wavelength of any radio wave at a given frequency f is going to be longest in free space. It'll be shorter in any media for which mu 0 and epsilon 0 are not equal to 1. If you're working with material where mu0 and epsilon 0 are, I'm sorry, UR and epsilon R are both equal to R, or U and epsilon are both equal to mu0 and epsilon 0, then the phase velocity in that media is equal to C, and the wavelength is the same as it is in free space. I'm going to call it a day. This is a board full of equations here, but you go a little bit early. We will actually finish up the textbook on Friday, so congratulations, pat yourself on the back. It's not often you make it through an entire, well, this textbook was actually designed to be covered in a semester, but even so, it's an accomplishment to get through any text, I think, in a semester. What I'll do is, please, well, the last exam will be open text, but I need to collect your textbooks on the last day of the class. So make sure that you bring them. If you would like to buy it, it's not that expensive. I'd have to check the price, but I think it's under $30 or around $30 or something like that.